All right, so today we're going to be talking about 2D raycasting and line segment intersection. In terms of how that fits into the course, there is going to be a part of assignment 4 that you have to use some of this stuff for. And as well, you can use it on the project as the lighting component. So we'll see how that all works out. But first, who's heard of raycasting before? You may have heard of ray tracing. Okay. So raycasting is, it's a name for a technique which has many, many different applications in games. Everything from where does this bullet land to really complex lighting and graphical effects. And if you've ever heard of ray tracing is sort of iterative ray casting. And that's used more so for graphics than for anything else. I'll have a few examples of that. So intuitively, ray casting is I'm going to cast some ray, meaning a straight line, in some direction. And where does that line intersect or reflect or bounce or have some sort of interesting interaction with the environment? That's the sort of thing that we do when we do raycasting. And it's very heavy on the vector-based math, but it has many useful applications. And what we'll be doing in this lecture today is not any of those super complicated things. So for example, if you want to get more and more complex with raycasting or ray tracing, you look at examples from either photography or video games where they're talking about like all these RTX on memes that happened a couple of years ago where you can simulate ray tracing in some of these games where essentially you have some sort of camera, you have an image plane, and then you're either bouncing rays of light from a light source off of object through the image plane, or you're casting these arbitrary rays sort of from the eye of the person in the game through each pixel of the image plane and trying to see what color or that pixel should be. Lots of complex math. Actually, it's more, instead of complex math, it's like a lot of applications of very simple math, but it adds up to be a really complex system. So in terms of actual ray tracing in a graphical sense, this is sort of what's happening here. You're trying to figure out which pixels should be which color in the image plane, meaning what should be shown on the monitor based on the geometry and the properties of surfaces. Like does light reflect off this thing? What is the color of that light? What is the light source direction, et cetera, et cetera. And for ray tracing, again, which we're not going to be doing, I just like to give this sort of example. Basically, like the more rays you cast, the higher resolution this image will be. And so I think this is an example from Minecraft. With its ray tracing capabilities on newer graphics cards, where you keep increasing this count. I don't know exactly what SPP found for. I just stole this GIF offline from somewhere online. But basically you see that as we cast more and more rays, we get more and more information. And it's like more and more light hitting a camera sensor if you're a photographer. Like if you have very, very little amount of light, you'll have a very little amount of detail. There was a very, very famous example of ray tracing that this was with one of the original Amiga computer systems. And it was this was a ray traced demo that was running on that, which had very, very realistic and accurate glass ray tracing effects, which is one of the properties that you can assign to things in the image. So this was figuring out in real time from some light source what the colors of things should be. And you can also see like how the world distorts in those globes. It was quite impressive at the time, even though, this person is made out of spheres. This is the person that's in all those physics problems, right? They're made out of spheres. There's no air resistance, all that kind of stuff. And modern day ray tracing uses the exact same principles, but we just have much more processing power now. And the really cool thing is you can get all sorts of extremely lifelike and accurate results by using ray tracing. But now that I've hyped that up, we're not going to be doing any of that. This isn't a graphics course. It's not a math course. I just wanted to show you that ray tracing is a thing that exists. But we will be doing raycasting for other purposes in this course. Essentially, what we're doing when we have raycasting is we're drawing a line between 2 points. And technically, that is called a line segment, because if you remember math at all, a line is technically an infinitely long thing, right? We have an equation for a line. It goes from negative infinity to positive infinity for x, and then you plot its y value. But when I say line in this lecture, What I actually mean is a line segment, a finite length line segment that we can represent by a starting point and an ending point. Because if we just draw the line between the start and the end, then that's our line segment. And then what we're going to do is we're going to detect if and where any collision occurs between that line segment and other things in our game or in our scene, etc. And there are interesting things that we can do with that. And then ray tracing is sort of this iterative approach where instead of just where did it intersect, it's also like where did that bounce, and then do that with the new one, and then do it with the new one, etc. But again, we're not doing that. So if no collision occurs on a line between 2 points, then they can see each other. So if you're familiar with, first-person shooters or military terminology, this would be line of sight, right? So I can see all of your eyes in this room right now because there's nothing blocking, but I can't see your eyes anymore if I hold up my hand because there's no literal line of sight or LOS between us. So line of sight calculations are something that you can imagine are very important in video games. So 2D raycasting, and again, most of the math from our 2D version of this also extends into 3D. It is just an extra variable, and like usually where we do 1 multiplication, it ends up being like 3 multiplications if you're doing it in 3D space. So 2D raycasting is going to primarily solve problems that deal with light or visibility in our games. In terms of lighting, what we could do, and I'll have better examples of this later, is let's say we have this little scene here with a few boxes, and we have denoted that these boxes will stop light from passing through them. So we could shine some sort of light source from here, and it would we would figure out somehow that there's supposed to be light in this area, but not supposed to be light in this area. And then on top of that, we could, enhance this with different graphical effects like coloring the lighting, putting shaders on top of this, etc. But we're just going to stick to the basic stuff for now. There's a really great tutorial on this website, Red Blob Games, when it talks about visibility, and they use much the same math that we're going to be using here today. So if you want sort of an extra tutorial, that link is there for you. It'll be in the slides. And later on, we'll be using one other website as an example for, their website had a really good example of how to use this math for lighting effects. So I've recreated their demo in PowerPoint slides, but I've also linked to it. And I'll link to that when we get to it. This is a really cool example that I saw from a game called Third Eye Crime by Moonshot Games. So what you do is you play this thief down here. You can just see he stole these jewels. And these guards or thugs or whatever they are, they're walking around in the level trying to catch you, right? So this game shows you the cone of vision that's being projected by these people, basically what they can see in the level. And as long as you can stay out of those cones, you can pretty much do whatever you want, right? It's just like if you were a thief in real life. If someone can see me, I probably shouldn't do that thing. And so there's some unique mouse controls here where you can sort of drag this path and you walk along it, etc. But that's just a cool example that I found of a game actually really using these line of sight calculations. Now, of course, there are lots of other ways that you could use line of sight calculations. For example, if there was a turret in the game. So lots of games like Portal is my favorite example of this, where they have these automatic turrets, and if they can see you, they'll shoot at you. But if they can't see you, then they won't shoot at you. And so it all uses the same type of mathematics. Here's an example that I did, which I will explain in great detail how I did this at the end of the course, but this is just done in SFML. And this is a really simple example that it's not like, it looks like light, but it's not light. I've just colored the regions that share a line of sight with my fake light source that's being moved around here in yellow. I've colored those regions in gray and the other regions in black. And in fact, what I did was I colored the whole thing black, and then wherever light should fall, I just create triangles, which I'll show you how to do later, in gray. So, but it looks like a lighting effect, right? It kind of looks like you have a flashlight that's being shined out and all sorts of different things. So there's really cool effects that we can create, and I'd like you to do one of these type of effects for the final project. So let's look at the basics here. So raycasting in its most basic form just asks, okay, I have a 0.1 and a 0.2, right? And is there anything blocking the path between these 2D points, right? So here, for example, we do have an example where there's something blocking the path between them. And so another way to ask that is, if I have this as a line segment and this as a line segment, do those two things intersect? Right? That's the question that we're trying to ask. So how would we detect that mathematically? Well, the path between 2 points is blocked if the line segment between them intersects with another existing line segment. Now, of course, there are shapes that we can describe, like curves or circles, etc., that don't fit into this line segment type of thing. But the games that we're making for this course, we're not going to go into every possible physics calculation for all types of shapes. This is going to work out for the games that we're making. So if we draw a line between P1 and P2, so this would be called line segment starting at P1, ending at P2, or if there's no direction, it's just P1, P2. And then we have another line segment here. We can see with our eyes that yes, if we were starting at P1 here, and we tried to, like, for example, shine a light or shoot a bullet or whatever it was, it would stop right here because there is a line segment between them. Now, I'm saying here we're asking if there's an intersection, but you may also want to know where that intersection occurred. So for example here, depending on the application, we may also want to know if the first, we want to know where the first intersection occurred. And why? Well, for example, if all I want to know is if P1 can see P2, then answering the Boolean question, is there an intersection, is fine. Just, can I see this person? But if I'm doing something more complicated, like where should the bullet hit, then the bullet is not going to hit this person, sure, but it's also not going to hit this thing right here. It's going to hit the first one. So calculating not only if there's an intersection, but where that intersection is an equally important problem. So in this case, it would hit this first obstacle or wall or line or whatever it's representing in your game, and it wouldn't be traveling on through that. So in this course so far, we've been talking about this vec2 class, and that represents points in 2D space as this 2D vector with an x and a y. So you've all done that for assignment 3. And a line segment can just be defined by the start and end point of a line using a vec2. So again, this is a line segment that has a start and an end, or I guess 2 endpoints. We don't always consider it to be a start and an end. But what I'm saying here is this is not an infinite line in y equals mx plus b form. This is just 2 points that define a line. So let's bring back the old Euclidean plane here. And again, just to let you know that even though this is the more standard math plane with 0, 0 in the bottom left, all the math still works out for your assignments and everything, even though SFML flips the y. All the math is still fine. So let's look at point A and point B here, and these are going to be stored as our vec2 class. And now what we have is the line segment AB. And so line segment AB, what can we do with that? Well, there's a bunch of different operations that we've learned on it so far. Let's just try first, let's subtract them, right? So if we take B and subtract A, then what this gives us is R. That is a vector that, if it starts at A, will point directly toward B, right? So mathematically, we can say that B is equal to A plus R, right? So if we take R, we start it at A, by adding it to A, it will end up at B. Okay, so we've all seen that. What we haven't done yet is introduce a scalar factor. So let's scale R by a scalar. So if you've ever wondered why, they're called vectors and scalars, a scalar is literally just scaling something. So in the case of a vector, it would be, if we scale it, meaning we're going to multiply it by a floating point value or a real value or something, then what we do is this vector is going to stay pointing in the same direction, but it's just going to get longer or shorter, okay? Because we're just multiplying those values. Now, if we multiply it by a negative number, it could also point in the opposite direction. But its starting point doesn't move, just the end point would move in this case when we're doing that. So in the case of B being equal to A plus R, then our scalar here would just be 1. So this is 1 times R, but let's, that's not very interesting. So let's introduce here a different scalar. So for example, if we took R and cut it in half, right? So we have 0.5 times R. Then if we took A plus 0.5 times R, then this would be a vector that's still pointing directly at B, but it only goes half the distance, right? Make sense? Cool. And what would happen if we made our scalar greater than 1, what would happen then? Yep, so it would just go past b, right? And if we made it less than 1, it would turn the vector around and it would point outside of b. I don't actually have a slide for that though. So in this case, if we take t and r, which t equal to 0.5, that's our scale factor, then b, we know we would get to b if t was equal to 1, right? So if we have that equation and we're trying to find t, then b is equal to a plus t times r when t is equal to 1. Okay, let's introduce another line segment though, so this gets a little bit more interesting. So before, we had r as the vector and t as the scalar. We're just going to increase those letters by 1. So we get, so r was the vector before. Now this vector is going to be called s. S is going to go from c to d, and our scalar on that vector is going to be called u. So r and s are the vectors, t and u are the scaling factors. So let's add another line that goes from point c to point d. So s is going to be equal to d minus c, just like r was equal to b minus a. And then we're going to scale s by some scalar value as well, and we're going to call that u. So at some point, if we could somehow find the correct value for these scalars, such that these two vectors pointed at or ended up at the exact same point, then what we would have is their point of intersection, if one exists, right? So let's find the correct scale values for r and s that make them meet. And if they meet, then we're going to have their point of intersection for those two lines. So for example, I've drawn this example just so that when both of those scalar values are equal to 1/2, then both of these vectors point to the exact same point in space, and so that is going to be their intersection point. So if we had some math oracle that could solve these equations for us, and we said, what are the scalar values so that these two meet, then we would get t is equal to 0.5 and u is equal to 0.5. So we have b is equal to t times r, and d is equal to c plus u times s. So the lines intersect when this value of b and d are equal, right? So whenever we want to have two different things, when we set them equal, we just take the equations that make them up and we set those equal to each other, right? So if we're trying to find where they meet up, that would mean that b is equal to d, so we have this is going to be equal to this. So we'll just put that down. And then the important part is that the lines are going to intersect if both t and u are between 0 and 1. Okay? The reason they have to be between 0 and 1, do I have a slide on this? No, I don't. Is because if it was less than 1, then this vector will be pointing in this direction, right? And if it's pointing in the opposite direction, then we're not interested, we're really not interested in any intersections that happen outside of this quadrilateral, right? Because they are not where the actual line segments themselves intersect. So those are the values, is they have to be between 0 and 1 to make sure that the intersection point is in here somewhere. That's just the way we've defined the lines. So we set those two things equal to each other, but so what are our unknowns here that we're trying to solve for, if anyone's been paying attention? Right? T and u, right? So what is the problem now if we try and solve for t and u? Yeah, right? So we're going to have at least at least the same number of equations as unknowns in order to solve for those things. But we only have one equation here, and we have two unknowns. So what can we do? Well, we're going to introduce a little bit of math that someone figured out somewhere who was really smart. And so we'll do things to both sides of this equation until one of the variables that we're trying to solve for goes away. And the thing that's going to allow us to do that is something called the 2D cross product. So before I get to the 2D cross product, I'll mention quickly the 3D cross product, because the 2D cross product is not a thing that's used a lot. So the 3D cross product, denoted A cross B, is an equation that doesn't really matter for this course. It's just a few additions and multiplications. But if we have two vectors, A and B, in a plane, then the 3D cross product is going to produce a 3D vector. So the output of the 3D cross product is another vector. And that vector points orthogonal to both A and B. So this is called the normal vector to A and B. And normal vectors are very, very important in 3D graphics when it talks about shadows, volumetric mapping, lighting, all sorts of things use this normal vector. And so it's a very important calculation, and some computer hardware actually has like hardware dedicating to solving this equation because it's so important. It doesn't make the same sort of sense when you're talking about what is the 2D cross product, but the 2D cross product, the formula for that, A cross B, you're going to take the x of A, multiply it by the y of B, and then subtract the y of A times the x of B. So you're subtracting the opposite of what just happened. And this produces a scalar value, so it's just a single number that this produces. It's no longer a vector that it produces. And from this diagram over here, the value that it produces is if we take A and B, and we extend these lines, so we take A and add it to the end of B, and we take B and add it to the end of A, what we get there is a parallelogram. And the scalar value that's output by the cross product just happens to be equal to the area of that parallelogram. So that's geometrically what it represents, but that's not important for our particular purposes. We don't have anything right now where we're concerned about the area of this parallelogram. But because it is the area of that parallelogram, this first property exists. And this first property just says that anything cross itself is 0, right? Why? Well, geometrically, that's intuitive because we can't form a parallelogram with ourselves. It would just have area 0, right? But mathematically, it makes even more sense, I think, because if A and B were equal, then we'd have x times y minus y times x. So that's always going to be 0 for any normal mathematics, right? The second property, which is the distributive property, which holds for multiplication in our normal numerical system, but it also holds for the cross product. And so I'm not going to derive that here, but essentially if you have two vectors, A plus R, and you cross that by S, then that's equivalent to crossing A by S and adding crossing R by S. So that's the distributive property. You just take the outside thing, you bring it into both of the inside things. So we're going to use these two properties now to help us with this equation that we didn't have enough equations to solve for our unknowns. So that's the equation again. And we're going to here apply the cross product of S to both sides of this equation. So what do we get? Well, we take this and we cross product it with S, and we take this and we cross product it with S. Now we take that distributive property and we go inside. So we take the S, cross product it with A, we get this, plus T times R cross S. Excuse me. And we do the same with the other side. But what do we have now? We have an instance here of S cross S. And we just said that S cross S, anything cross itself, is going to be 0. So this term here, no matter what U is, that's always going to be 0. So we can eliminate it. And now we're solving for T, and we just have one equation with one unknown. And so we've eliminated the U from the equation, and we can solve for T. And we're just going to start by taking this and moving it to the other side. So we have C cross S minus A cross S. And then we can use the distributive property to simplify that and just say C minus A cross S. But this is still only equal to T times R cross S, so we're going to divide that, right? So we take, since the output of the 2D cross product is a scalar, then we can just do this division. So we're going to have this scalar here divided by another scalar, and that's going to be equal to the value of T. And now we do the opposite thing if we want to solve for U. And so instead of cross-producting both sides with S, we're going to do it with R. And I'll just go a little faster this time. We cross both sides with R. We apply the distributive property. We remove the thing that has value 0. And like before, now we're going to have a value for U like we had a value for T before. And so that's the pretty simple math that we can use to solve this. And since this is one of like the only instances of math in the whole course, this is probably a question about this could appear on an exam, right? It's not super complex. I probably won't get you to do this entire derivation, but I mean, it's not too difficult if I do ask something like that. But something I may ask during the exam might be, here's the values for these 2 points, find the intersection point, something like that. So we've solved the intersection. We have t equal to this and u equal to this. Now, okay, is this fine? Yeah, we could all put that in the code. That's no problem. But I like going a little bit further and trying to make this a little bit more computationally efficient, if we could. Here's another property, which you could all figure out if you wanted to, I'm sure. But r cross s is equal to negative s cross r, right? Because there's a subtraction inside. So if we flip the terms, then we bring the subtraction outside, and it works. So, okay, why do we care about this? Well, this lets us rearrange some stuff above. So wherever we have s cross r, we could change that to r cross s and introduce a negative sign. And up here, we have a minus c both crossed with something, so we could also rearrange this and introduce a negative sign. The negative signs then cancel each other out. And so we're going to rearrange these so that instead of u being a minus c cross r divided by s cross r, we do that thing where we introduce a negative sign on the bottom to flip these terms and a negative sign on top to flip these terms. Negatives cancel out. So now what we have is u is equal to this. But you might say, okay, we still have the same number of operations. Why did we do that? Well, it's for the following reason. Now we have t is equal to this and u is equal to this. And we can see c minus a is actually used twice now, instead of having one a minus c and one c minus a, and r cross s is also used twice. So what we can do is at the beginning of this computation, we can just compute those two things once and then read them as a variable rather than compute them twice. So this is just a little tiny optimization that things hopefully run a little bit faster. But something that's very interesting that can really only be solved by experimenting is, does this actually save you time in your game engine, right? So whether or not eliminating, so what is 1r cross s? That is 2 multiplies and a subtract. So does creating another variable in memory end up speeding up your code faster than 2 multiplies and a subtract? That's actually not, due to pipelining and the way that that's parallelized by your CPU, even though it's not parallel code, it may not actually save you any time. But what you would do is implement both and then test and see whichever one is faster, that's the one you end up going with. But I still like showing you this because theoretically it should be faster. Yeah, that would be up to you to see. And so this is the final version. We have t is equal to c minus a cross s divided by r cross s. U is equal to c minus a cross r divided by r cross s. There is an intersection if and only if t and u are within 0 and 1 inclusive. And then once we solve for t and u, we plug t and u back into the original equations to find the intersection point. And since the intersection point, there's only one intersection point, then we could either do this equation or this equation. Because if there's an intersection, they will produce the same value. So if we want to find that intersection point, once we've found t and u, we can do either of these things. Okay? So if we want to put that into code, how are we actually going to implement that in our assignment? Well, I'm actually going to write the code for you here, almost exactly how we'll write it in C++. So I'm going to have a little struct. Again, a struct is like a class that everything is public, so it's just a collection of data. And two things that I want to answer about line intersection. One, is there an intersection, right? And if there is an intersection, where is that intersection? So the very first thing here is a bool. That's going to be true or false, whether there's an intersection. And the second thing is a position. Now, you might say, okay, why are you doing this when things like standard optional exist? So standard optional is a thing in C++ that in situations where you have a Boolean and a result, you could use a standard optional to store the result, but if there is no result, then it will just be null, and you can just check it, right? So there are things you can do that are a little more clever in modern programming languages to get around this, but why not just do this? It works, and there's not really a performance hit to doing this. So this will be our function. So it'll be called line intersect, and you'll be writing this function for assignment 4. It takes in, again, this is not pure C++ because I didn't have enough room to type it all in, but it takes in 4 vec2s, A, B, C, and D, representing line segment AB and line segment CD. we're going to compute r, which is equal to b minus a. And of course, because our nice vec2 class has these operators, we can just do things like subtraction on these vectors. Then we'll compute s, which is d minus c. And then my float rxs, that's going to be equal to r cross s. And so maybe in your vec2 class, you would want to write a function there called cross. Or you could even define multiplication between two vectors to be the cross product if you wanted to. So however you end up writing this down or implementing, it doesn't really matter. And then c minus a, cma is equal to c minus a. And now we can implement that formula. So t is equal to cma cross s divided by rxs. U is equal to cma cross r divided by rxs. And then if the values of t and u are both between 0 and 1 inclusive, then I will return that there is an intersection, and it is this intersection. So this is just the x and y value of that formula of a plus t times r. And if the values are not between 0 and 1, then I would return false, and then the second one doesn't even really matter, right? Because we're not going to be using the intersection point of an intersection that doesn't exist. So that's it. This is your line intersection function. That'll tell you if two line segments intersect and where they intersect. I'm not claiming that this is the most possibly efficient version, but it's the most efficient one I've found so far. If anyone comes up with something better, please let me know. And I will gladly change my slides to something that's easier to do. So now that we know how to do line segment intersection, how do we use it for visibility? Well, it's pretty easy in this case. If line segment AB does not collide with any vision blocking entities, then B is visible to A. So if there's some line somewhere that does intersect, maybe with, let's say, the simplest possible thing we could do in assignment 4, which we'll end up doing, is just take the midpoints of the NPCs and the player. Right? Now, technically the midpoint I can still see around, like I have two eyes, it's up here, I could technically see part of me that's not the middle of me, but we're not going that in depth with it. We're just going, can the center of the NPC see the center of the player? And also, if we have multiple intersections, now we might have to do something where we want to say, okay, if we need the information of, say, where does this light land, or where does this bullet land, what we would have to do is compute all of these intersections and then take the resulting vector that has the shortest length, because we know that would be the first such intersection. So maybe we calculated this one first, then this one, or maybe this one first. We would just have to keep track of the shortest of the intersections. What about non-linear game objects, like things that are just not simple lines? Well, it turns out that in our game, they're just made up of lines, right? So what we can do is if we have two rectangular entities and we want to know if that entity blocks the vision of this thing, then we would just do all four of these, right? In a very sophisticated computational geometry class, there may be some sort of data structure that allows you to do this slightly faster, not having to check all four, but I haven't found a good one that is suitable for this course yet. So if you have these entities, just figure out the line segments of the edges of the entities, which you can do by taking their midpoint and their length and their height. You figure out those line segments, and then you calculate whether or not this line intersects with this entity. So for example here, this is where it would stop. And in assignment 4, we are going to be writing two functions. One of those two functions is the the line intersect function, so you'll be writing this. And then we'll also have an entity intersect function, which is going to take in an entity in our game engine and a line segment. And what you're going to have to do is take that entity, figure out the four corners of the entity, so A, B, C, and D. Then you'll take the line intersect function, and you'll take, does this input line intersect with the top of this entity? Does it intersect with the left of the entity, with the right, or with the bottom? So that's going to be the entity intersect function. It's going to call the line intersect function 4 times to see if it intersects with any of them. Okay, so you can now see how this can start to, okay, for bullets, it's obvious. Like if I shoot a bullet in this direction and it's a hit scan bullet, hit scan meaning it's instantaneous rather than a projectile, I can say whether or not B will be hit by a bullet from A, right? Because it'll hit a box, so it won't hit them. If it's a projectile, then this is different because projectiles will move and then collide eventually with something. But what about lighting effects? Light travels out in all directions, right? So how can we calculate everywhere that light lands? So for example, how could we implement this demo that I gave a little while ago? Just letting that play for a little bit just to give you a feel for it. Okay, so we're going to do that example now. We're going to do all the math for it, or at least I'm going to give you a high-level description of it. So light travels out in all directions. How do we calculate everywhere it lands? There are several possible options. There are actually many, many, many more options that we could possibly have time to discuss in this in this class. But what we're showing are the ones that are feasible for implementation in our games. This website right here, ncase.me/siteandlight, this website is excellent and it goes through the math. It's similar to what I've said already, but it's a little bit different. But it does give the same demo that I'm about to show a bunch of different steps on how you would accomplish this. Now again, just as a caveat, this is not the only way to do it, but it's a nice balance for this course. So there are other ways that you can do it, and for the final project, I'm not limiting the way that you do this thing. I am just concerned with you doing it by yourself, right? So you take some math and you implement it on your own rather than just asking some AI or getting some other library that does this for you. Okay, so let's say we have an environment like this, where we have each of these objects, and these objects are just going to be polygons, right? They're not regular, they don't have to be concave or convex or anything, they're just polygons, and the lines of these polygons are going to be blocking light. Okay, so that's the environment in which we're living. So the very first thing we're going to do is cast a ray. So we're going to cast a ray from some position in some direction. And we're adding the additional constraint that the way we make this not infinite is just by saying that, okay, our ray is also going to stop at the edge of the screen. So there's 4 additional lines, the top, left, right, and bottom of the screen itself. So we're adding those as an additional thing that they can intersect with. So if we cast one ray here, then it will intersect not with any of these obstacles, but with the side of the screen. So if in this demo on the website, we cast a ray toward the mouse pointer, what we can do now is we can calculate, since I've given you the math to do this already, you could just say draw a line from the middle of the screen toward the mouse pointer and find out the first thing that it intersects with and stop drawing the line at that point, right? We've already done the math that's necessary for this. But, of course, if we have some sort of light bulb, it's casting rays in all directions. So how could we do that? Well, we can't do infinitely many things, right? But what we could do is just cast more rays, right? So we calculate some number of rays that we would like to cast, and then say, okay, let's say I'm casting, I don't know how many are on the screen here, maybe 20. Let's say, let's have some math that's really easy for me to do. So I'm going to say, oh, we randomly decided to cast 36 rays. So we would take 360 degrees, chop it up into 10-degree segments, and then just cast rays in those directions. And what we would get is something that starts to look like what we're looking for, right? You can see that the areas that are covered by the lines are places that the light would reach, right? So you can start to see how this looks really cool. Where now we have instead of shining a ray from the middle toward the mouse pointer, in this demo, the mouse pointer is the source, the light bulb sort of thing, and we cast rays in all directions. Now, the next thing we're going to do is turn all these lines into triangles so that we can draw them with some sort of color or texture or whatever. So we would turn those things into triangles. And now, when we move our pointer around, we can see the area that these triangles are covering. But who can see, like, what's sort of wrong with this? I can see someone else. Yeah, anyone else? Yeah, so what does that, like, it looks bad, right? It's sort of accurate, but as you can see, some of these corners are being cut off, and there's like this sort of jittery effect. And I'll get back to that in a second. But first I want to explain, how do you actually make these triangles? Well, step 2.5 then would be something called a radial sort. So, as you generate these vectors, you're probably generating them in a way that like either goes clockwise or counterclockwise, right? You're saying start at degree 0, add 10 degrees to that, make the next one, add 10 degrees to that, make the next one. So if you've generated them in that way, then all your points are already stored in a radial sort, meaning that they are stored in your vector or in your collection, however, increasing by angle rather than by length or something like that. If you haven't done that, then what you would have to do is sort them yourself. So if you didn't generate them in a sorted way, and the sorting here would be, okay, I have this line here at 0 degrees, so I'm going to take every line and figure out its angle between this point and this line. And then what I would do is I would sort all of the points radially like that. Once you have a radially sorted group of triangles, or a group of points, then what you could do is you could say, okay, triangle 1 is between point 1, I guess let's call this point 0 in the middle. So point 0, point 1, and point 2. That's the first triangle. The second triangle is between the next number. So 0, 2, 3. The next one is 0, 3, 4. The next one is 0, 4, 5. So that's how you would define the triangles. But it turns out that most graphics libraries understand that this is a thing that we want to do pretty often. And so they have introduced this thing called a triangle fan. And a triangle fan is a set of triangles connected to a central point. The first vertex is the center, and each new vertex defines a new triangle using the center and the previous vertex. So over here, this one sorts them clockwise instead of counterclockwise. But if we just specify these points as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, it will draw all of those intermediate triangles for us. The only thing is, if we haven't sorted those points radially, either counterclockwise or clockwise, it doesn't really matter which one you do, then the triangles might be like flipped and inversed, and some of the things might look weird. So make sure you radially sort those. And what we get is from our line segments and the endpoints of the intersections, now we get these triangles. But as we saw before, there is some jitter here, right? It doesn't look exact for some reason. So how could we solve that? What's the cause of that jitter? So the cause of the jitter is the following. As you said before, we're sort of skipping over some corners. Well, what does that mean? Well, I've chosen some sort of degree of separation. I can't cast infinite lines, right? So I have to cast some sort of lines. And what happens is this following scenario happens, where I have one line on one side of a corner that's not intersected, and then a line on another side that is intersected. So if I try and draw these triangles, this is a case where this triangle, do I have a slide for that? Oh, I do. So if I draw this triangle, it actually goes through an object, which is not good. That's one case of it not being good, because I'm shining the light on top of this object, which shouldn't happen. The other case where it's not good is this sort of undercutting, where the triangle, it actually, our light now doesn't reach the object. So there's two of these possible cases that we want to avoid. And so this is what we end up having. So in our demo that we gave, this is a still frame from that. We can see this happening all over the place. So we would cut here. We maybe wouldn't have enough here. This one here would be a weird triangle that goes from one shape to another one, etc. And then we have these triangles now going on top of this, which we don't want to happen. So all of these triangles here would be malformed triangles that either go over things or not enough things. So what's the solution to this? Well, one thing you could say, well, computers are discrete things, so just like circles are a bunch of lines, maybe we could just cast more points, right? Well, casting more rays, it turns out, gets really expensive, right? We don't want to cast thousands and thousands of these things. But the thing is, no matter how small we create them, we still get this problem. The problem just becomes smaller and smaller. So is there a way to eliminate that problem? The actual solution that you can do is to realize, okay, the only places in this scene at which light should intersect things, so go past it or not go past it, are at these vertices, right? We very rarely care about what happens between those vertices, right? So between here and here, we don't care about those things because they're all just hitting this. Between here and here, well, they're all just hitting the wall, right? But we also have to make sure that we cast to the other vertices that are not the intersection points, right? So we have to cast toward all of the vertices that we have in here. But what this does is now I don't need to worry about whether or not I have 20 rays or 2,000 rays. I just have to cast rays to these vertices. But there's an issue with this as well. How do I make triangles out of these now? Right? Okay, I've identified these sort of inflection points or something like that where I only care about the behavior changing, but this isn't the triangle that I want to draw, right? I actually do want this to sort of go past a little bit. I want it to miss by a little bit so it'll go past. So here's what we do. For each line that we draw, and again, this is not the only way to do this. This is just one way to do this. For each line that we draw, we're going to cast 2 other lines. So we're going to triple the number of lines that we draw. We're going to draw one slightly to the left and one very slightly to the right. I've grossly exaggerated this here, right? You'll be going like such a minute, like fraction of a degree to the left or to the right when you do this. The important thing here is now that one extends beyond the point, which is exactly what we want to happen, right? So one should extend beyond and one should not extend at all. But if we did have the case where we did this one and we extended 2 more rays, well, all of those rays would just hit. So it wouldn't really matter, right? So this gives us a ray at a very narrow angle that extends beyond the corner like we would want to. And so what we do is for every single ray that we cast to all the vertices, we also cast 2 more slightly to the left and the right. And what we end up with is something like this. And so yes, what we've done is we've now made the lighting problem as complex as the number of objects in the scene, rather than some arbitrary amount of floating point precision we were wanting ourselves to deal with because we wanted to use 10,000 points or something like that, which is good. Typically, we want the accuracy of things to be dependent on the complexity of the scene, not other things. And then if we take these points and we make triangles out of them, and now we know how to make those triangles, we can see now that these triangles are not going to be overlapping any of these points, and they're not going to be undercutting like they did before. So what we end up having is this much, much smoother effect, actually using fewer line segments than we were originally using when we were just casting rays in every direction. So now what we can do is that we have the geometry of the scene. Here, I'm sort of doing the opposite of lighting. I'm actually, the whole thing is white, and I'm coloring it in where these triangles should be. But I'll just leave the rest of it sort of up to you, right? Like, how would you turn that into this, right? So this is directly from that sight and light demo, where now, oh, look at this, there's almost like little shadows there. So we could even detect, you remember when we casted the 3 rays, the 2 extra rays? Well, if we take the triangles formed by those extra rays and we give them like a slightly lighter color, then this is almost like some sort of shadowy effect. Not complete darkness, not complete light, but in between. So in here, what you could do, this will become a lot more obvious when we talk about what shaders are, but here, like they made the whole scene black and then drew the triangles in white, which just makes it look like you're shining a light. But now we know sort of under the scenes what's happening here. There are rays being casted to all of these things. It's very, very fast calculation, and then we're just drawing the rays there. You could also think of doing cool things with shaders like they have there, where you have this sort of effect, right, where you are uncovering some sort of secret based on whether or not the light is shining on top of it. But That sort of thing is out of scope until we get into shaders and how you could take those triangles and apply some shader to it, etc. You could also have, you don't need to have polygons to do this. You could just have arbitrary lines in your environment. I know this is a bit hard to see here. It's a little bit nicer on my screen here. What we could do, maybe you have a turret that spins around in a direction. Now you know how to do this, right? So these are all the areas that that thing can see. But what we've done here is we've given like some sort of directionality to the vision. So if instead of just casting rays in all directions, you cast them in this cone, whatever the field of view is of this NPC or turret or whatever, now you can get these sort of effects that we saw in this Third Eye Crime game. So you could all pretty much take just the stuff that was in this lecture, and it might not have as much polish, but you could make a game for the final project that has this same sort of mechanic where someone is looking for you, they're turning around, and as they turn, all you got to do is like cast those rays. Instead of going in a full circle, they're just in a little cone. And then of course, so we start like something like this, then we go to maybe something like this with a little bit more of a lighting effect, then we go here, so we get a little bit nicer, and then eventually, we can add all sorts of crazy stuff. Now, I'm not saying that you can do all of these effects with just the math here, but this math is at its heart literally what we were just doing, right? So, Jesus, I finished the lecture. Okay, so that's it. Yeah, I know. I don't need to stretch it out just to meet the class all the time. I actually introduced a few slides there, but then I took the website that they had and put it into PowerPoint, and that made things much easier to explain. So cool, I can put a little bit more into the lecture for next year. But just remember that, so this is what we're going to be doing, basically this for assignment 4, not a cone, but we're just taking 2 NPCs, and then I can't pause this, but pretend, let me go back into here. Let me, oh geez, where's my use presenter view? Okay, so let's say I have, this is the NPC, and this is the player character. What we'll do is we will, let me get fancy here. All right, so we'll draw a line from the NPC to the player, and then for every one of our tiles in the game, we're going to figure out the 4, like for example, does it collide with this tile? I'm going to figure out the start and end points of the 4 corners that I've drawn terribly, and see, well, does it intersect with the top one? No. Does it intersect with this one? Yes. I can stop. So what we'll have in assignment 4 is we'll have an NPC with a follow behavior, and if an NPC is tagged with the follow behavior, then if line of sight exists between the center of that NPC and the player, it will just start moving toward the player. But you can start thinking of all sorts of game mechanics surrounded by lighting effects. Like if you've ever played like Luigi's Mansion or any of these games, you have a flashlight. If you shine the flashlight on someone, they freeze or turn invisible or whatever. And so you can think of all sorts of cool weapons that operate like this as well.